So in today's world, the ability to interactively run ad hoc SQL over petabytes of data is becoming very important. And there are multiple of use cases, business use cases that want that. Now, if you look at the kind of queries that run in this environment, a majority of them are OLAP style. So basically, we are computing aggregates over some things like transactions, clicks, revenue, products, downloads, so on and so forth, across multiple of dimensions. And the data that is accessed by these queries is both historical as well as recent data. Now, several big data warehouses have come up recently because there were limitations of the existing OLAP technique. So for example, we could not just use OLAP queue because the number of dimensions are too many in the big data sets. We cannot just use caching because a lot of these queries are ad hoc in nature. So the data may be too big to fit in, or it may not have gotten access before. Sampling techniques, again, with the ad hocness, they could be any number of predicates or in any order of columns getting accessed. So there's the big data warehouses that have come up, like, for example, Dremel or BigQuery from Google, or Presto from Facebook, Impala from Cloudera, and from IBM, there is Big SQL, Big A effort going on. All these do not manage the storage directly themselves, the raw storage. Instead, the data or the table as shown here is stored in the underlying file system. It could be Hadoop file system or classes or a GPFS in case of IBM. Now, a component called data serializer and deserializer sit between the query engine and the file system, which read the data. So I mean, basically they convert into the format that is required, and then they read and write and return the relevant data to the query engine. Here, storage plays a very important role. So we would, to have very high query throughput and also be able to address the ad hoc queries, we want to be able to read less data and read it very fast. Right, so the data is residing on the storage. It may not be cached or anything like I mentioned earlier, and we just want to run the queries right on the data in the file system. So with that, and there are multiple of efforts going on, like some in the query engine to optimize the query side, or the engine, or have tons of scale out as the Dremel and all do to address interactive analytics. We're looking specifically into the storage side of the things, just because of its importance. And now one option or question is like, can we leverage Flash here? And this community knows better than anyone else the advantages of Flash. So I don't really have to go over all this. But the main thing is that if we have a hierarchy of Flash and DRAM, like a combination, we can do it cheaper and as better or slightly less better than having just pure DRAM solutions, which were mandated by a lot of solutions recently for doing an interactive analytics, including at IBM. So that is one thing which is very attractive. The other is the non-volatility. So we do not, in a caching-based solution, we have duplication of data, which is not a very good thing in a big data scenario. So if we just have one copy, it really helps. And that too in a very fast-performing tier. So we can leverage it as both a primary tier and an extended cache. So in this paper, it's looking at doing it as a tier, and there's work going on for the extended cache part. So there's several challenges. Like one of the option to just leverage Flash is to, let's say we figure out that this is a popular data, and we just move it from the hard disk to the Flash, right? But now, if the data has been laid out in a very hard disk specific fashion, right, and it's accessed using a lot of sequential accesses, and random accesses are not used, and so on and so forth, we can only leverage suboptimal performance gains for the amount that we are spending on the Flash in this scenario. So we need to do something better. Like so our the layouts and the algorithms have to be more optimized for Flash. So, and the other thing is that while Flash, as you all know, that it has very high random access performance, but the sequential performance is not that great compared to the disk, right? So if you're looking at the performance per dollar, then random part makes much more sense. And the other thing is that Flash has been leveraged very heavily in the OLTP transactional point query kind of environment or update heavy environment, and there has been a lot of research work there on how to basically solve the random write problem of Flash and have more optimized indexes and for Flash and so on and so forth. But in the OLAP world, there has been very limited work, and it's there in the paper. And on SQL over big data, it really hasn't been looked into. So is there really an opportunity there? Because typically in OLAP, the tables are just scanned sequentially, and all the columns are just scanned fully. So that's one of the big questions here. Now, if you look at the current big data warehouses or the current serializer and deserializer, the way they work is, let's just take a very simple query in which we are calculating an average of over column C3, where, and the predicate for column 1 is 121 and for column 2 is 501. So what they do is they, in the selection phase, which is the where side of the second side of the query, the entire data for the column 1 and column 2 would be read and sequentially. And the data in gray is the data that is getting read. And if you notice that actually very little data is really relevant to the query, but everything just gets read. Then a predicate match is done, and it's basically just 3 row IDs out of all this data that match both the predicates. And then in the projection phase, again, the entire data for column C3 is read, and then finally those 3 rows are projected. So there is nothing like late materialization or anything which has been used in other database fields in the projection side to just limit the data read in the projection phase, right? So clearly there is our opportunity here that we can leverage to skip the data, read less data, and also hopefully read it faster. So another look at this shows the selectivity, which is the number of rows that match the predicate for each and every column, selection column, in TPC-H query 6, which is ad hoc business analytics benchmark, decision support benchmark. So if you look at, for example, L-ship date, only 15% of the rows are actually relevant to the query, whereas the current systems would read the rest of the 85% data also. And if you look at overall, after matching all the predicates, only 1% of the data is really relevant. On the other hand, the existing systems would read the 99% data for all the projection columns. And the more the projection columns, more is the irrelevancy of the data that is being read. So clearly there's a lot of option. So overall, these are the limitations of the existing data layouts and the algorithms of the serializers and deserializer we have in this world. They're optimized for HDD, for the hard disks, so they do not really do a lot of skips, which would have let them get rid of all this irrelevant data. Then all the row groups, everything is processed serially, right? Not much parallelism there. And projection side, there is no late materialization. It just read all in once, and it requires a lot of large memory footprint, right? Because if you're reading so much data. And recently, just late last year, ORC file was introduced in which it does some skipping, but at a very coarse-grained level. And I will show a comparison with FlashQueryFile and ORC file in just a minute. So overall, our solution is a flashed, optimized FlashQueryFile. And what it does, it leverages the random IOs, like the zero-seek latency of Flash, to do very fine-grained intra-row group level skipping of the data. And when I say row group, basically in these columnar store formats, the data is laid out sequentially, right? But then it is horizontally partitioned into row groups, and each row group would contain thousands or millions of row IDs, right? So we are basically looking both intra as well as inter-row group skipping. And in addition, the algorithms use the high internal IO parallelism that we can get with Flash as opposed to hard disks. So it's both skipping as well as making it faster. This compares is with the state-of-the-art ORC file. So in case of ORC file, the data here in the column, the one in gray is the one that is read, and the white is the one that is skipped. So if you look at the top one, in case of ORC file, it may be able to skip a complete row group, but it doesn't do anything within a row group, right? And this coarse-grained skipping works on very limited conditions. Like for example, if the column is very high cardinality and it's sorted, then we would get very effective coarse-grained skipping. But a lot of columns are not like that. In case of FlashQueryFile, we're doing both the coarse-grained skipping, just like ORC file, as well as intra-row group fine-grained skipping. And also everything is read in parallel and to leverage the I/O parallelism that we can get from Flash. Now, clearly there's a lot of challenges here. Like we cannot just do random accesses because there is overhead associated with that. So we have to have a right balance between the sequential and the random calls. Secondly, skipping of the data is quite intuitive in the projection phase. And there is a paper that has done that in the past because you already know the row IDs of interest. So you can just go to them and fetch the data, right? But if you look at the selection phase, it's not really as intuitive because you have to figure out the places where the data exists in the, or there's a predicate match in the first place, right? And typically you access the whole thing and then you read it. And we cannot just, other thing is that we cannot just have the same layout because the column cardinality, sort order and everything does have a play into having a more optimal layout. So, and the last thing is that if we have all these layouts and everything, but if our code is really meant for hard disks, so for example in Java and all, you can have all the file system APIs by default are buffered, right? They are, so instead of that, if you use a direct I/O or if you use more asynchronous I/O, more effective memory management and everything, then you can really get the benefit of all the layouts and algorithm changes. So in FlashQueryFile, basically, the data is not just placed as is, unlike the other layouts. Instead, it's optimized for selection as well as projection. And the coding and everything is much more in line with the Flash characteristics. So prefetching is not done, direct I/O used, asynchronous I/O is used, and so on and so forth. And the details are there in the paper. So just to look into the selection optimized side. So here what happens is like a dictionary of the data of the unique values is created and is serialized onto the file. And all the row IDs where the unique value occurs is then serialized onto the file block. And in terms of the selection algorithm, so first let's just take this example of a simple query. So first what happens is just the dictionary portion is read, so which could be very small if the cardinality of the file is low or high if, right, vice versa. So next we do a predicate match, and in this case two of the values would match the predicate, and then we just read the row IDs that that basically match those unique values. So now you can see that we have skipped quite a large amount of data that happens, and we are only able to read the data that is relevant to the query. So this provides us a mechanism to do fine-grained skipping even in the selection side, in addition to the projection. So just another illustration. So this is like ORC File, which is a default, and we are just looking at one row group instead of looking across row groups. In case of FlashQueryFile, first thing, let's say we have a situation in which the predicate just doesn't match for one of the queries. So after just reading the little bit of dictionary, we are able to skip the rest of the data for the other columns and also the row IDs from that column. And if the predicate matches only few row positions, we are able to skip that row positions that do not match the predicate. So we are able to skip quite a bit of data. On the projection optimized side, we maintain a row ID to the dictionary index lookup. So in the projection algorithm, basically we would just, and we do late materialization. So we do not do the projection algorithm till the selection algorithm has finished. And we have the row positions of interest. And at this point, we just skip and read the row positions of interest. And if the row positions of interest are together, then we cluster them. Otherwise, they are randomly accessed and read. So again here, if the selectivity of the query, like if very few row positions match, so for example, if that the list that comes into the projection algorithm is a very small list, we can get significant gain both in speed up and as well as data reduction from this phase. So now to move on to the evaluation. So FlashQueryFile was compared with ORC File, and in which case ORC File does coarse-grained data skipping. And the baseline here is the RC file, which doesn't do any skipping and just reads the entire data as is. And all of this was compared, I mean, even though we did a lot of comparisons with other queries, but here I'm showing the results with query number 1. In this, the x-axis shows a selectivity, which is the number of rows that match the predicate. And it was important to show that because the results are sensitive to the selectivity of the query. On the y-axis, on the primary y-axis is the speed up of the query. And on the secondary y-axis is the data read by the query normalized to ORC file, right? So here, if we look at a selectivity which is less than 1, the less than 1% rows match the predicate, we get a major speed up of 100x compared to ORC file. And the data that is read is, it's like 0.0012% of what was needed, what was read in by ORC file. If we go to 58% selectivity, where 58% rows match the predicate, then we get an 11x speed up, and the data is closer to the 58%. So, I mean, we do have some overhead, but not a whole lot. So, we were able to reduce the data by almost 35% in case of 58% selectivity. So, you can see that we are skipping the irrelevant data, and we are speeding up the query. The speed up is coming from 3 ways. One is the reduction in the data. Secondly is the parallelism that is used. And third is the efficient coding as well as data structures and layouts. So just to dig deeper into this and just show a breakdown just in the selection phase, right? Because that is something which has never been looked at before. How do we get a speed up there? So this is compared to ORC file and then baseline. This is again for query number 1. So ORC file is not is reading the same amount of data as the baseline, and the reason being is that their coarse-grained algorithm is not able to find any row group that they can skip, and that's because the predicate is actually very the values are very finely distributed uniformly distributed across the column, and there is nothing that really any row group that doesn't match the predicate. On the other hand, in case of FlashQueryFile, the data is reduced significantly, and only 20% of the data is read and the 80% is skipped. And that is because of the fine-grained intra-row skipping that we are able to do. And in case of ORC file, we were not able to take advantage of the coarse-grained skipping. So just to conclude, I know everybody wants to go out faster. So in this, our goal from the storage layer was that we should be able to read less data and we should be able to read it faster, right? And for this, we wanted to see if we could leverage Flash in the stack. And there are, based on the experiments and the analysis, like there is a lot of opportunity for leveraging Flash in the OLAP or in the big SQL or the SQL over big data world. And if we just use techniques in which we place the HDD-optimized layouts or algorithms, and we just place them onto Flash, we would get very suboptimal performance, as the results show, right? In which, in that case, ORC file, which is HDD-optimized, was just placed on Flash. And we could see that we got a 11x to 100x performance improvement by using a Flash-optimized version. Secondly, in case of the Flash optimized layouts, like we should be able to leverage both the random IO and the internal IO parallelism as much as possible to be able to do very fine-grained intra-row group skipping. Just the coarse-grained skipping of the row groups doesn't really cut it, and there's a lot more opportunity for doing fine-grained. In addition, we can change the selection and the projection processing and make it much more faster so that we can achieve our goal of reading things faster as well. And in this paper, we presented ways to lay out the data in the file itself so that when we are reading it, even if the data is not cached or anything, we are able to do the query very fast right on the data, right? And this is very important for ad hoc queries in which you have no idea what kind of a query could be running and where is the data in the cache or not. And lastly, just because we're able to reduce the data that is read per query so much, it reduces the memory footprint requirement, which has become a big concern amongst the customers, and by the amount of memory footprint that is required by a lot of the solutions. And secondly, it also reduces extreme scale out that is needed by solutions, just so that they can get the I/O bandwidth that is needed for processing these kind of queries. Yeah. So thank you, everyone. At this point, I would like to take any questions.
Not racing to the mic yet, but they all will. Even if you're not a database weenie, you can race to the mic. But being a part-time database weenie. So, okay, I'm going to try to go through a little bit of history here. So we implemented special purpose data warehouses because OLTP databases were too slow at warehouse queries because you had to go through a lot of data, and so you clearly wanted to organize it so you could go through it sequentially. So now we have these data warehouses. But it seems to me what you're saying is, hey, guess what? On Flash, that doesn't hold. You don't need to go through things sequentially. So my question is, what happens if you start running OLAP queries on OLTP databases on Flash? Because you said OLTP is already nicely optimized for Flash. It does lots of random stuff. You get indices, so you don't need to do a lot of this stuff. You can shred your rows into columns, so you get the columns. So why not just throw away the data warehouse structures and just say, we'll do it on the OLTP databases, and then we only have one code base to maintain?
So there are a lot of issues there. Like one is the scale. So even the OLTP databases that are out there, they do not really scale to the level that is needed here. So that is one thing. And the second thing is that in case of here it's majority of the data is read only and everything, right? And you're not really doing any of the point queries, or you're not doing updates. So why have all the overheads and everything that come from that into the space?
The system is well designed. If you're not doing updates, you're not paying for the cost of the updates. And I'm guessing, I'm just guessing that no salesperson inside of IBM would ever say that their OLTP system does not scale to handle workloads of this size, because I can guarantee that the Oracle guys won't say that either.
Right. No, definitely. Actually, the whole, this work is going towards a unified system. So I'm just presenting one part of it, but the goal actually is to have a unified system in which we are able to do the OLTP and OLAP on the same things. But the details and everything is not really worked out as well. Just the focus is on, yeah. But we can take this offline. There were a lot of other